CLion, a cross-platform IDE for C and C++. Download now.
Okay, I think we should start. Hello, everyone. My name is Pavel. Let me focus my slides. My name is Pavel. I want to talk to you about JSON in C++ and specifically about designing a type for working with JSON values. So in this talk, we'll discuss a quick overview about JSON, design for a C++ type for working with JSON values. So basically, this talk is a case study for designing a type for working with, in this case, JSON values. We'll cover standard containers and std variant and how to work with them. And at the end, we'll add support for C++ allocators to our code. To make this talk a little bit more interesting, I have some constraints. For example, I want to use C++ 17 in 2025. I believe not everyone can use C++ 23 or even C++ 20. So we will have this constraint, and I think it will not abstract us too much. Another one is I want to write as little code as possible because you can write thousands and tens of thousands of code to implement something, but more interesting and difficult thing is to write as little code as possible, but at the same time maintaining reasonable design and performance. That's the challenge. And not in this talk at this time is JSON string escaping, serialization, stringification, and parsing. All of these topics can occupy several talks, several hours. So unfortunately, at this time, we will not cover them. So a little bit about JSON. Why JSON? It was specified by Douglas Crockford in early 2000s. The actual RFC is 8259. And you can see example of JSON values on the left and meaning on the right. For example, null is like absence of value. True or false are Boolean. We treat them as Boolean values. You have numbers, you have strings. All of these are primitive types according to the specification, and I will call them scalar types. And also you have arrays or sequences of values, and you have objects or dictionaries, which are called structured types according to the specification, and I will call them collection types. And one more note why JSON and not some other format is because I think JSON grammar is very easy. So I took all the grammar from the RFC and put it on one slide. And my claim is that you don't have to read everything on this slide, but my point is that I can have all the grammar on one slide. For comparison, this is, I would ask you in person, what is this? You can make a prediction in your mind and see if you are right. This is YAML or YAML. It's like more than 100 pages, and almost all of that is grammar and specification of grammar and how to treat the syntax and semantics of that. For comparison, this is all the grammar from the C++ standard. And again, for comparison, this is the entire RFC of JSON format. Besides the grammar, it has, for example, table of contents and references and whatnot, and other considerations and discussions, and all of that much smaller than any of the other things. This is how I propose to map JSON types to C++ types. True, false, for example, null is the absence of value. We'll get to that later. True, false is kind of obvious, is Boolean. Maps to bool. Numbers we want to map to int64 and double because these types have different ranges of values and have different properties. For example, int is exact representation, has exact representation of the values of the numbers, and double has an exact representation. And depending on the actual value that we want to represent, we want to choose one or another. For strings, it's obvious to take strings as to the string. For arrays, we get as to the vector of value, the value being the value type that will conceive in this talk. And for objects, it's reasonable to get an ordered map because the specification says that the keys and values, key value pairs are unordered. And so it is optimal, in my opinion, to map that to an ordered map. A little bit more on the strings. In C++17, we have char, which is almost, I said, I would say virtually on all platforms has 8-bit width. And henceforth, we can use the string, which is specification for specialization of basic string for char. In C++20, we have char 8, which is guaranteed to hold at least 8 bits, so it can accommodate for UTF-8 code units. And we have specialization of basic string for char 8, which is U8 string. But even though we have that, even in C++20, I would probably advise to use the string still, because in my opinion, interoperability between the string and U8 string is less than perfect, let's say that. And having U8 strings, you will have a hard time interoperating with all the code and all the interfaces, which we have plenty. So my advocacy is for using the string anyway, even though we have U8 string. So JSON value is a union type, so-called. It can hold different types of actual values. So it is natural to use std variant from C++17. For absence of value, for null, we have monostate, then bool, then int64, double, string, vector, and unordered map. All the types that JSON types map to that we discussed before. So let's define our value type that will represent JSON values in C++. And here we have aliases for our convenience, that is null, boolean, string, array, object, and finally variant that has defined variant with all the alternatives that we want to use to represent JSON values. And in private section, we have a data field of type variant. So we would love to write code like this. For example, we want to use default constructor. We want to use a construction from values, different values. And to accommodate that desire, we need to define constructors. In this case, we have default constructor with the default implementation. We have a constructor from arbitrary values, except from value itself. To restrict this constructor from taking values, we have to have enable if t, and we are able to put it right into template parameters because we can, and because actually we have no other place to put it to, and practically, and this is okay. This is safe, and you can do this. And of course, here we want to make sure that we don't allow values of type. We don't want this constructor to accept the value itself. So we introduce this check here. Remove cvref_t is shorthand for remove cvt, remove reference t, because C++17 have no shorthand for that, and we introduce it ourselves. And of course, in C++20, besides remove cvref_t shorthand, we will use requires instead of enable of t. And this looks a little bit more presentable and easier to read. And if you would write it in C++20, you would use requires instead of enable of t. So in the implementation, we just forward the value that we got to the data field, to the construction of the data field. I have no exact specifications here and throughout the slides, but they are not very relevant to the design, so I will just gloss over them and ignore them. But I have it on the slides for completeness. And the other constructor that we have to have is a constructor from string view, because string view has no implicit conversion to string. And if we haven't had this constructor, we would not be able to construct our value from string view. And I think this is natural thing to do, to construct a value from string view and expect that we have a string type inside our value. So we have to add this constructor as well. In the implementation, we use in place type constant to specify that we want to construct exactly string type inside our variant, and we just pass the value. Next, since we had constructors, we have to have assignment. And here we have assignment from arbitrary value. And here we have to have enable of t as a return type. We could have enable of t as a template parameter, but then we will allow some maybe evil people or not so evil people to be able to write the code like at the bottom of the slide. This is not so bad, but people can explicitly specify template parameters, template arguments, and we don't want to allow people to write this not very let's say correct code. We want to our code to be easily used correctly and hard to use incorrectly. And this is not entirely correct type of usage, in my opinion. So for that reason, we have to have enable of t as a return type. And in C++20, of course, you will use requires instead of enable of t, and value will be naturally as a return type. And in C++20, it looks a little bit more presentable, as I said already. So in the implementation, we just assign the value, we forward the value and assign it to our internal variant and return this natural, I think. The same applies to string view, the overload with string view. We have to have it to be able to assign from string view instances. And again, in the implementation, we just use emplace, specifying that we want to construct a string inside our variant and return this. Pretty natural things, I think. So so far we had some constructors, some assignment operators, and I have a question for you. I think we can have a poll. Which rule did we use? Did we use rule of 3? Did we use rule of 5? Did we use rule of 0? And do we have a poll? Yes, we have a poll. So I have a cheat sheet for you. Rule of three is when you define destructor, copy constructor, copy assignment. Rule of five is when you additionally define move constructor, move assignment to the three above, and rule of zero when you define none of the above. And let's give the audience some time to vote. We have some votes. Votes are coming. So far, rule of five is in the lead. But overall, votes are uniform, more or less. So let's end the poll. And we have rule of five in the lead, then rule of zero, and then rule of three. And people who voted rule of zero are correct because, in fact, none of the constructors and assignment operators are copy constructors or copy assignment, or move constructors or move assignment, because we specifically used enable of T to restrict the constructors and assignment operators from accepting the value itself. And using rule of zero, we essentially ask the compiler to generate all the necessary special member functions for us, namely destructor, copy constructor, copy assignment, move constructor, and move assignment. So this is rule of zero. Next, we can have equivalence and not equal operators, and in C++17 we have no choice but to explicitly define them. In C++20, of course, you can ask the compiler to generate default implementation for operator equal, and operator not equal will be synthesized from operator equal. And of course, we have variant methods to access the variant, the actual std variant field that we use to store values. And we have conversion operators, because why not? Notice that for R value specified methods and operators, we have to use std move. So at this point, we are done for now with value itself. Outside of value, we can have aliases for our convenience for object, array, string, boolean, null, and variant itself. And finally, we can write kind of useless or not so useful code, let's say. And here we visit the variant that we get from our value using std visit and using widely known in narrow circles overloaded pattern. This is the overloaded pattern is just like 2 lines of code, even 1 line of code if you are using C++20 conformant compiler. The overload object that we create here copies of the lambdas inside itself. And when we visit the variant itself, the subsequent lambda body is called according to the type that the variant has. So here we basically, for the given variant, depending on the type that it holds, we can print either the type or even the value that it holds. So let's try the code that we have to this point with decently recent compilers, in this case ClientKT and MSVC from Visual Studio 2022. And for Boolean, for the program that you can see at the top of the slide, the output can be Boolean true. Okay. For string, we have output string hello Boolean true. Wait, Boolean true? Huh. And for numbers, MSVC refuses to compile with error. Let's figure it out. The thing is that in C++ 17, initially, alternative is chosen as if by overload resolution of the functions that you can see at the middle of the slide. So basically, the alternative that the variant chooses to construct is determined by the resolved overload of this overload set. So for example, for true, like at the bottom of the slide, you have call to test bool. For hello string literal, you have call to test bool again, because string literal decays into pointer to const char, and the best overload in compiler's opinion is test bool for that, and test 42, which is int literal, doesn't compile at all, because the compiler can't decide which is the best overload for that, either int64t or double or even bool. So we get the error of ambiguous call. This nonsense was fixed is in proposal 0605 or 0608, but Microsoft left the original behavior in C++ 17 mode because it motivated it, people motivated it by backwards compatibility. But we want our code to work with a little bit older versions of Microsoft standard library and C++ 17 mode as well. So we have to have a workaround. In this case, this is basically copy-paste from standard library code. We check if we work with MSVC compiler. We calculate the maximum of MSVC lang and C++ constants. And if the maximum basically is equal to 2017-03, that means that we are in C++ 17 mode in MSVC compiler and standard library. And we have to have a workaround, except that Microsoft decided that P0608 behavior will be unconditional in C++ 17 mode in recent releases of Visual Studio and MSVC compilers and standard libraries onward. And so we have to add this clause to not enable our workaround when it is not needed for recent compilers. So here we have our workaround. It is not very complicated. We add two overloads for const char pointer, in which case we construct a string, and overload for int, in which case we construct int64, and similarly for assignment operators for const char pointer overload, we just call in place specifying that we want to construct string, and for int we call in place specifying that we want to construct int64 and pass the arguments to the in place function. Okay, now with our workaround, all the code with all the compilers, with all the supported standard library implementation works the same way. That's great. Now let's discuss how we initialize our values. So here is an example, basically copy paste from Niels Lohmann's library documentation and Lohmann JSON. Here you can assume that we want to construct an object with the appropriate keys and values, but I have I don't like how it's done here. Let me explain why. So for example, here we at the top of the slide, you can see the code where we construct a value with outer braces, inner braces, empty braces, and we print the result to console. In this case, we'll get an array with one value null. Okay. What happens when we add one value inside inner braces? In this case, we have another behavior. We have an array inside an array with one value, a string value. Okay, this is the second behavior. What happens if we add one more value? Now we have the third behavior, all the arrays go away, and now we have an object with one pair of key and value. Okay, what happens if we add one more value inside inner braces? We get to the second behavior. Now we have array inside an array with three values, and honestly, I don't like this inconsistency. So we don't have to do anything actually, because all we have to do is to explicitly define or specify collection types. In this case, object, which is a alias for an ordered map, and array, which is an alias for a vector, and that's it. We don't have to do anything else because all the work is done with by developers of the standard and developers of the standard library implementations, and we just can use an ordered map or vector constructors, and everything else is done for us. I think it's great. So now let's return to implementation of the value interface. We would like to inspect values. For example, we would like to ask if this value contains an object, and if it does contain an object, we would like to ask for a reference to the object by way of as object member function. And the same is for array, the same is for string, the same is for double, the same is for int, the same is for Boolean, and the same is, or kind of the same is for null, because null implies that there is no value, so there is no reason to try to extract or get value from the from our value. The actual absence, we don't want to get the absence of value from our value, if it makes sense. So using this inspection interface, we can write code like this. In this case, we assume that our JSON is an object. We ask for a member with key array of that object. We assume that that resulting object is an array, and so on. This code is terrible. We don't want to write code like this. So let's again see what other libraries propose. And again, we'll see example from Niels Lohmann's JSON library. Here we have, Niels proposes to use subscript operation. In this case, we use list string to get the next level of our JSON object, and we use 0 index to get the element with index 0. Again, using subscript operator. Again, I don't like how this is implemented because, for example, if we have our JSON object constructed by default, it holds null by default. And if we use the subscript operator with 0 index, for example, magically variable x now contains an array with one null value. Okay. Alternatively, we can try to subscript it with a string, and now the object that was null contains an object, an actual object, with one value pair with key foo and value null. Okay. Ultimately, we can write code like this. This code is, we know that this code will compile and throw an exception. We know this beforehand, but we still can write such code. And again, we don't want to, we want our code to allow to write correct code easily and to write incorrect code impossible, or the harder the better. Well, I butchered that phrase. I think the correct phrase is we want how's it goes? We want to allow to write correct, easy to write correct code and hard to write incorrect code. That's it. So my feelings about this code can be summarized with this picture. And if you criticize, you have to propose something. And I propose to have a resolve member function. I hope it's kind of intuitive how it works. Some examples here. We can have one or more designators or parts of tokens that we want to use to resolve eventual object in the structure of our JSON value. For example, if we use first string item, we imply that X is an object, and we're trying to get the first value pair with key items, and with the second index 0, we imply that what we got from the previous step is an array, and we are trying to get element of that array with index 0. The other way around, for example, if we assume that y object, y value is an array, we are trying to get element 0 from that array. And from that result, from that step, we are trying to get value with key foo in that object. I hope it makes sense. We can have arbitrary number of arguments to that function. For example, if we want to get to the fourth level in our JSON document, we can have 0, which gets the element with index 0. Then we are trying to get value with key foo. Then we are trying to get value with key bar, and then we are trying to get elements with index 2 from the array that we got on the previous step. Or otherwise, we can use just one argument, in this case 0, that implies that we want to get element from the array with index 0, or index 1 for that matter. In that case, we'll get the second element. And otherwise, if we can't resolve a value in our JSON document with that signifiers or specifiers, the function will return null pointer. We can check that null pointer, and that way we'll know that there is no such value in our JSON document with that pointer. This is very similar to JSON pointer. That is also a specification that you can look up. So let's implement that. For that, we have to have two functions that will make our lives easier. For numerical index, we have the first overload. Here we try to get an array from within our variant. If we got an array, we check that the index is within the array bounds. If it is, we return pointer to the element from that array with that index. Otherwise, we return null pointer. For string key, we do similar thing. We try to get object from within our variant. If we got an object, we try to find a member with that key. If we are successful, we return pointer to the value of that member with that key. Otherwise, we return null pointer. And Here's the user facing function, user facing member function, resolve. Here we for C++17 use enable if t to constrain the function that in the way that we want to have one or more arguments, and we check if every argument that it is convertible to either a number or a string. In C++20, of course, you have more presentable way of writing this. You have requires instead of enable if t, you have normal return value specification, and here is how the check for conversion of the arguments is implemented. Here we check that the argument t is convertible either to string or the size t. We use not equals as an exclusive or in this case. And in the implementation, we initialize a pointer to value with this instance, and using old expression, we iterate over every reference token or argument or specification of each level that we want to traverse, and assign back what we got from the resolve input. So at each step, we get either the next traversable value or we get null pair. And logical AND short circuits this calculation in case we got null pair, and this works great. Except that we have to explicitly cast it to bool because some compilers complain that we use assignment instead of equivalence comparison in a logical expression. And we also have to cast it to void because some compilers complain that we calculated some value and never used it. So to silence that these complaints, we have to have these conversions, explicit conversions. We got the const variant. We can have non-const variant, non-const overload for that by using the const overload, resolving the value, and casting away const from the result to casting to value pointer instead of const value pointer, and returning it. So in this, what I said, that way we don't repeat the implementation. We know how the const implementation works, and this allows us to use the const implementation to implement non-const overload. And here's how we implement resolve member function. So we are almost done with our value type. We have slight nuance, is that at the point where we define the aliases for array and object, value type itself is incomplete, and actually we use this incomplete these definitions with incomplete type to define IO variant and to define the member field of type variant. This doesn't work in every case because vector, according to standard, the vector has to support incomplete types, but another map that we also use does not have to support incomplete types, but de facto it supports in all major standard library implementations, except for libstd C++ versions earlier than 12. And we want our code to work with the libstd C++ versions earlier than 12, so we have to have a workaround. In this case, we instead of just having variant field, we have to have a workaround field instead. And here how we can implement it. We have a dummy unordered map. In this dummy unordered map, we use array, a complete type, instead of value that is incomplete. So in this case, unordered map with array is complete type. We use that dummy unordered map, which is complete type at this point, to define dummy variant type, which is also complete at this point. And we guess that our dummy variant and our production variant, so to speak, have the same alignment and size. And here we use this guesstimate, so to speak, to define the storage for our production variant. Here we don't use aligned storage as the aligned storage because it was deprecated in C++23 because it is underspecified. And instead we use an array specifying alignment and size explicitly. So here we go, defining the rest of our workaround type. We have a default constructor. Inside we use placement new to construct variant. In the storage, we have a copy constructor in which we use placement new to copy construct variant in our storage. Similar to move constructor, we use placement new to try to move construct a variant in our storage. And we have a convenient constructor, template constructor for arbitrary values, in which we use also placement new to construct a variant from arbitrary values in our storage. Okay. Next, we have a destructor in which we static assert that we guessed correctly that size and alignment of our dummy variant is the same as our production variant. We put these checks in the destructor because we assume that destructor probably will be compiled always, because at some point you need to destruct value, and you'll have to call the destructor. The destructor is compiled and the check will be checked. And also in the destructor we have the explicit call to destructor of the variant. Also we have assignment, copy assignment. Here we just convert ourselves to reference to variant and assign. We have move assignment, in which again we convert ourselves to references to variant, and move assign, try to move assign. And again, I have a question for the audience. Let's try to have another poll. Let me try. Yes, thank you. We have another poll, and the question is the same. Which rule did we use here? Rule of 3, rule of 5, rule of 0. And here we have, okay, we have two leading variants, two leading alternatives, one of which is rule of 5 and one of which is rule of 3. Let's give a chance to vote for people, just a few more seconds. I can remind you that rule of 3 is when you have copy constructor, copy constructor, copy assignment and destructor. Rule of 5 adds to that move assignment, move constructor, and rule of 0 says that we define none of that. We don't define any of that special functions. Okay, I think we can end the poll, and the leading alternative, rule of 5, will lead the poll, and you are correct. Let me get the focus back to my slides. Yes, you are correct. We used rule of 5. We defined copy constructor, move constructor, we defined destructor, we defined copy assignment, we defined move assignment. This is 5 special member functions that rule of 5 is concerns. So let's finish discussion of definition of our workaround type. Here we have our variant conversion operators. Here, basically, we reinterpret cast pointer to our storage to pointer to variant, to our production variant, and return that reference to that object that we get from that pointer. So I don't want to discuss it in depth because this is kind of not very interesting and very technical stuff. So just keep in mind that we just basically use reinterpret cast to cast the pointer to storage, which is an array, to pointer to variant, and then return a reference to the object that our new pointer points to. And so thus we implemented our workaround, and we now can use our code even with libstd C++ standard library implementation that don't allow us to use unordered map with incomplete types. So the idea is basically that inside the implementation of the member functions, that all types are complete and we can freely use them, but at the point of the definition, we have to do something. In this case, we have a storage for the yet incomplete type, and I hope you got the idea. Next, we have visit, and here we just can use std_visit. Rather, we can't use std_visit as it is, because although our value has conversion to variant, std_visit is a template, and this template cannot understand that actually our value type has conversion to variant. So we have to explicitly convert our value to variant, and then we can use std_visit. But I think it would be nice to just write visit, and for that we can implement our own version of visit, and I propose to do that. We want to model std_visit in its behavior, and to do that, to figure out how it works regarding arguments, we have to parse, in this case, CPP reference documentation, and after we parse it, we figure out that std_visit can accept either std variant itself or a type derived from std variant, from a specialization of std variant. So I will show you only C++20 version of the implementation of visit. It's not hard to write it for C++17, but just more code, and actually we have no time to go through that extra code. So here in C++20, we use requires to constrain our function to only accept values that are derived from base value type. We'll discuss it a little bit later. We have decal type auto return type. We have our visit template definition, function definition. Inside the function, we calculate the actual base type, and then we call std_visit, and we use that base value type to call exactly the variant member function from the base type. So even though we can get a type derived from our value type, and this derived type can have variant member function that may do something else. We don't want to call the variant member function from that derived type, and so we have to specify explicitly qualify that we want to call the variant function from the base type. So to the calculation of the base type, we can have declarations, two declarations of function overloads. In this case, get value, which receives anything, literally anything, and another declaration that receives a const reference to value. This second declaration have a high priority, and it will be invoked for any type convertible to const reference to value. So by calling get value for any type, either we get the first invocation for literally any type, but if the argument is derived from value, we'll get necessarily the second invocation, invocation of the second overload. So having that, we can just have our alias defined like this. We decal type, using decal type, we calculate the type of the return type of the get value. To get value, we supply some argument that is some arbitrary type without const volatile and reference qualification. And in this way, we are able to figure out whether any type is derived from value, publicly derived from value, or maybe this is some unrelated, completely unrelated type, in which case we get void, which is not value type. Let me discuss a little bit return values. So here, for example, we have auto return type, and here the return type, the actual return type is deduced as if by calling some function template like this, like you see on the screen. And when you supply return expression from the return statement to such call, literally the type that was deduced in such call for such template is substituted instead of auto. So similarly, for example, for const.ref return type, the auto type is deduced as if by calling template with the const t reference parameter type, and whatever we deduce for t, we basically literally substitute instead of auto. So this is good, but sometimes we want to use exactly the type of the return expression that we probably will not be able to be able to deduce with auto. For that reason, we can write decal type expression as a return type, but this is not always convenient or even possible. So to use as a placeholder, we can type decal type auto, and auto here is literally a placeholder for expression. So we in this case we deduce the return type as if applying decal type to the return expression. I hope this makes sense. So this is how visit is implemented. I think I have 5 minutes left, and I have to speed up. We have only allocator support left, so I will probably speed up through these slides. I'm sorry for that. To add allocator support, we have to have our value converted into a template. Here we rename our value into basic value. We add template parameter allocator. We have to rework our aliases definition. Here we have to explicitly state every template argument for the basic string specialization. Here we use rebound allocator as a shorthand for allocator traits, rebound alloc, to specify rebound alloc for the basic string. The same for array, the same for unordered map. we have to add some constructors. These constructors look like default constructor, copy constructor, and move constructor, but with added allocate parameter, and this allows us to be locked in, to be switched in so-called users allocator machinery. So here we use construct as a kind of factor out all the functionality that we need into for construction into constructs private member. Inside it, we check if the other variant is valued by exception. In that case, we have nothing else to do except forward the other instance outside to the construction. Otherwise, we visit the as other variant, and inside our visitation, inside our visitor, we calculate the type that we got. If that type is either object or array or string, we construct the new variant and pass allocator to the constructor. So the allocator is propagated to the types that are objects or arrays of strings. Otherwise, we have no need to pass allocators and we can just construct variants. Otherwise, we need to, or rather we can have a alias value specifying some allocator, for example, allocator from for char type. In this case, in this way, all the code that we wrote and use value will still work, and we have some default in order not to always use basic value, and we have to specialize users allocator in namespace std. So the users allocator, so-called machinery, is turned on for our value, so for our type. Otherwise, we need to again modify our workaround for incomplete types, again to specify all the allocator and other explicit template arguments. We have to modify our calculation of base type because we now have basic value template instead of just value. And we are basically done. Now we can define an alias, use, for example, polymorphic allocator, and to just use an alias PMR value in this case to construct a value. Again, in this example, it will use get default resource because we did not specify which resource for polymorphic allocator we want to use. And actually, adding allocator support was not so painful and bad. And this talk by Bjorn inspired me to do that, to add allocator support. We have one drawback for that, for this bizarre code that you can see at the top of the slide. For some reason, Clang with libstd C++ versions earlier than 12 gives us an error, some cryptic error, which basically says that value is not copy constructible. And I filed a bug for that error, and we can patch that error with this huge band-aid. And we can assert that, actually, value is copy constructible, and then Clang will be like, oh yeah, indeed, value is copy constructible, and will compile your code, and like nothing happened. So at this point, here's what we've done. We implemented variant like value for working with JSON values. We used rule of zero. We work around some bogus variant construction for initial, for which was initially for what was initially specified for variant construction and choosing alternatives. We implemented hopefully rich interface that's easy to use correctly and hard to use incorrectly. We work around some impossibility to use incomplete types, specifically in libstd C++ version earlier than 12. For that, we used rule of 5. We added allocator support and uses allocator functionality support, and work around some both Clang compilation bug. with libstd C++ version 12 and earlier. And instead of conclusion, I can say to you that one does not simply write a JSON library in C++. For those who are interested, you can check out MinJSON CPP, which this talk is based on. I have a challenge to write C++ library in 1,000 lines of code. I failed. I managed to write in 1,500 lines of code. This library has all the basic functionality. So if you want to check it out, you can just basically Google or use any search engine that you like to search for MinJSON CPP. And at this point, I'm done. Thank you. I think we have no time left. And I will answer questions in GatherTown. Are we done?